All right, today we're jumping into one of the biggest, thorniest problems in all of crypto, the fact that blockchains just keep getting heavier forever. And we're going to look at Kaspa's pretty wild solution, a system that lets it safely forget the past without losing even a tiny bit of security. So let me just throw a question at you. What if a blockchain could just run forever, process millions, even billions of transactions, but the actual data you need to keep it secure never really grows? I know, it sounds kind of impossible, right? But this is the exact problem Kaspa was built from the ground up to solve.
Okay, so to really get why Kaspa's approach is so cool, you gotta understand the problem it's solving. People call it state bloat, but I like to think of it as the blockchain's infinite weight. You see, for most projects, the more successful they become, the bigger the problem gets. Every transaction just adds another layer of permanent weight.
I mean, just look at the classic chains like Bitcoin. Every single transaction from day one is stored forever. And as you can see, after a few years, the amount of data you need to run a full node just gets massive. And this isn't just an inconvenience, it's a huge threat to decentralization. The fewer people who can afford the hardware to participate, the more centralized the network becomes. So the big question is, how does Kaspa get around this? Well, it's not some kind of black magic. It's actually built on two incredibly smart design choices that were made from the very beginning. These are the two key ingredients that make it possible to just delete old data totally safely. Let's break it down. Prerequisite number one is this super clean separation of data. Every single Kaspa block is split in two. You've got the block header, which is tiny but absolutely vital, and then you have the block body, which is huge but, as you'll see, kind of temporary. The absolute genius move here is putting a complete summary of the network's entire financial state right inside that tiny header. And that vital summary has a name. It's called the UTXO commitment. Seriously, think of it like a single, perfect, cryptographic fingerprint that represents the exact balance of every single wallet on the network at that one moment in time. By tucking this away in the header, Kaspa makes sure the absolute financial truth is always there, even if the bulky transaction data that led up to it is long gone. So you might be thinking, okay, how do you update that fingerprint with every single block? Well, that's where this really slick technique called muhash comes in. Instead of having to recount everything from the very beginning, muhash is way smarter. It just takes the last summary, mathematically adds or subtracts the new transactions, and boom, you have a new perfect summary. It's unbelievably efficient. All right, so that's piece number one, separating the state summary. But the second piece is all about playing chess, not checkers. It's about thinking way, way ahead. You see, inside that same tiny block header, Kaspa also includes information that basically pre-calculates how blocks are related to each other. It's like building a blueprint for a future structure that's going to be super important later. This is the seed of what becomes the super DAG. Okay, foundation's set. Now let's get to the fun part. Let's start pruning. Act 1 is all about the low-hanging fruit, getting rid of the heaviest, most bloated data first, and that means the block bodies. And the rule here is actually super straightforward. Once a block gets old enough and is buried deep enough in the chain, what's called the pruning depth, its raw transaction data just isn't needed for the network to agree on the present. It officially gets relabeled as data that the network is allowed to forget. So, poof, the giant block body, it's just deleted. Gone for good. But because that vital financial fingerprint, the UTXO commitment, is tucked away safely inside the header, nothing important for consensus is ever lost. The network stays perfectly secure, and its financial records are totally accounted for. Okay, so we've shed all that extra weight from the block bodies, but we're still left with this super long chain of all these little headers, and that's where Act 2 comes in. This is about taking that long history and consolidating it into something way more elegant and efficient, the super DAG. Now, to get this next part, you need to know about something called a super block. These things are really cool. Every now and then, just by random chance, a miner finds a block that is way, way harder to solve than the network required. These are super blocks, and they're like these massive concrete pillars in the history of the chain. They prove a huge amount of work was done right at that point. So just to paint a picture for you, this is what the chain looks like after Act 1. We've gotten rid of the bodies, but we still have this long, unbroken chain of every single header with these special super blocks mixed in. It's a lot smaller, for sure, but it's still a whole lot of data. And here it is, the final move. In Act 2, the system prunes again, but this time it deletes all the normal headers that are sitting between the super blocks. And remember that blueprint we talked about way back at the beginning? This is where it all clicks. That pre-calculated structure allows the network to just link the superblocks directly to each other, creating this incredibly compact structure, the superDAG, that still preserves the full security and weight of the entire proof-of-work history.
So we've gone through Act 1, we've gone through Act 2. What's the big payoff? What do we get for all this clever engineering? Well, we get something that's honestly a revolution for blockchain, a bounded history. And honestly, this is the part that should make you sit up and go, whoa. The total amount of data that a node needs to hold on to secure the network becomes bounded. It actually stops growing. That means whether the network is a year old or 100 years old, the storage you need to securely validate the chain stays about the same. That is a total game changer.
So what this means in the real world is that the default way to run a Kaspa node is pruned. It keeps the recent history, which you need, and that super compact superDAG for everything else. Now, anyone can choose to run an archival node and keep every single piece of data forever, but, and this is the most important part, it's totally optional. You don't need them for the network to be healthy or secure.
And the bottom line is, this makes the whole network way more open and accessible. A brand new user can download a node, sync up, and start helping to secure the network without ever needing to download terabytes and terabytes of old historical data. It just tears down one of the biggest barriers to entry.
And so all of this leaves us with this really mind-bending question, right? For years, everyone just accepted that blockchains had to get heavier and heavier forever. It was just a fact of life. But if that fundamental limit is actually solved, what does that unlock? What kind of speed, what kind of scale, and what new ideas become possible when a blockchain can finally and safely just let go of its own weight?